Okay, good morning, everybody. So we were discussing conditional probabilities last time. And related to that, we also discussed regular versions of conditional probabilities, in which case we can treat the conditional probability as a transition probability kernel. So conditional probability should act like a probability, meaning that as a function of the set, your input, it should act as a measure, as a probability measure. But on the other hand, since it is defined as a conditional expectation, it should also be a random variable for every choice of the set. So conditional probability is the object this, right? Conditional probability of B given G. And this was defined as the conditional expectation of its indicator given G. Therefore, it is a random variable. So it is a function on omega as well. So I can put an omega here, and make everything dependent on omega, so that it is a function of omega as well as a function of B. So omega is, so with respect to omega, this should be G measurable. So it should be a G measurable random variable. And with respect to B, this should be a probability measure. And as we discussed last time, there are issues with the G measurability of this when you pick one version of this conditional probability for every B. If you do it arbitrarily, you can have some issues. But if you have a regular version, it satisfies these properties. And this is the case if you have a standard measurable space. So for the existence of a regular version, you need to make sure that the sets B come from the sigma algebra of a standard measurable space. And using this construction, we also talked about conditional distribution of a random variable given G. So if you have some random variable, let's say Z, okay, taking values in some abstract space, so you're interested in conditional probabilities of Z taking values in certain sets coming from the sigma algebra of the measurable space that this random variable is taking values in. So we're looking at the conditional probability of this event. Okay, this is the event that we're looking at. Therefore, now this is a function of f. Let's say coming from some abstract sigma algebra H. Okay, so now this is coming from the image space, whereas here this was coming from F. This was coming from F, our sigma algebra on the probability space. Okay, so here this is the image space of Z. But again, we can just look at this as an event, right? This is an event in F. If Z is a measurable function, it is a random variable, right? Therefore, we can just take B as the event that Z takes values in F and define this conditional probability. And again, this is a function of omega as well. So this should be a transition probability kernel. So a regular version is a transition probability kernel from omega f into omega g into h script h. So a kernel L, let's say. So in this case, this should be L of omega n f, if you're talking about a regular version. And with this regular version, you can indeed use it for integration. So if you integrate a function h with respect to L, meaning that if you integrate h of z L omega dz, because this is a measure on, this part is a measure on h, right? So it is an integral over the space h. And because of the omega dependence, I should also put an omega here. So this is now a random variable. It is G measurable because the function part of L is G measurable. So this is a version of the conditional expectation of H given G. In other words, you can see it as conditional expectation of H of Z given G is calculated as H of Z times its conditional distribution given G. Given G. All right, so this is our notation for L of dz. Okay. I omit the omega part, as I don't put it explicitly. So it's a random measure. It's a random measure. So now we're going to look at a further special case of this. So conditional distribution of a random variable given another random variable. So for this, I'm going to use a random variable y, which is going to generate our g. So let y be a random variable with values in some measurable space E, and z be a random variable with values in H. So these two are just some abstract measurable spaces. So in this case, we consider this subsigma algebra generated by Y. So it consists of events of the form Y takes values in D, where D is coming from the image space of Y. We know that this is a sigma algebra. So we can just use this G in this setting to define the conditional distribution of Z given Y. So we simply define it as Z in F given sigma of Y. Okay, so the mapping is called the conditional distribution of z given y so a regular version of it is a transition kernel, transition probability kernel from omega g, now g is sigma y, into h script h. This is not a definition, this is just a remark, because the regular version is already defined in the setting of, in the general setting of conditional distributions given some arbitrary sigma algebras. So this is not really a definition, but I'm just commenting on that. And as we discussed this for conditional expectations given random variables, whenever you have something that is measurable with respect to y or sigma of y, we say what? If a random variable is measurable with respect to sigma y, what can you say about that? So this conditional probability is a random variable, right? It has an input omega here. So what can you say about this sigma y measurable random variable? So in general, which property does it satisfy? If a random variable is sigma y measurable, if a numerical random variable is sigma y measurable, what can you say about that? So for each f, this is sigma y measurable. Therefore, it should be something in terms of y, right? So it should be a function of y, right? So there should be some function, let's call it gf of y, for some measurable function gf defined on the possible values of y from e to r, let's say r plus or r bar plus, whatever. It's going to give you a probability, therefore you can bound it, but anyway. So it is, in fact, a function of y. We can say it. And indeed, we can also talk about the following. So if y of omega is little y, then we know that z in f given y at omega is going to take the value gf of y, right? So if it's a function of y, this means if you have two different omegas for which y of omega is the same, then for those omegas, the values of the conditional probability must be the same because it's just a function of y. So in fact, we may find the conditional probability of z given f, z in f given y equals little y as gf of y for every y in the E, okay, or possible values of y. So this mapping is called the, So for fixed y, this mapping is called the conditional distribution of z given y is equal to little y. So there is this language issue here. So this, as a random variable, is called the conditional distribution of z given y. And this is now what? Just some values, right? So this is the value of this is just deterministic because we're telling the exact value of capital Y. So this is going to be a probability measure, not a transition probability kernel, because we're fixing the value of Y. So we call it the conditional distribution of z given y is equal to little y. And they are pretty much the same thing, just a language issue. Okay. So let's write the conditional probability of z given f given y as, okay, so this was g of f of y. And I can also see it as a function of y and also a function of f, right? So if we work with a regular version of the conditional distribution, then this omega f maps to k of y of omega to f is a transition kernel, transition probability kernel. So the question is, can we see yf to ky of f? Namely, if we replace this by a fixed value. So is this can we see this as a transition probability kernel? Transition probability kernel from omega sigma, from so y is coming from E, right, into H. Okay. So to be able to answer those questions, we also need to look at the joint distribution of y and z. So to answer this question, we will have a look at the joint distribution of y and z, or the distribution of the vector yz. So now it's time to connect conditional distributions with joint distributions. And the key theorem is going to be the so-called disintegration theorem. Disintegration theorem. So remember how we constructed measures on product spaces. So let's say you want to construct a measure on the product of ENH and ENH. How did we do that? Well, we defined a product measure, a measure on the product space, as the product of a measure on the first space, measure on the first space, and a transition kernel from the first space into the second. And the meaning of that was, well, if you need to integrate a function with respect to pi, so you look at ky dz, you integrate over h, and then you integrate over e. Right? If f is a measurable function of the two variables. Right? For instance, if you have a measurable rectangle, the value of pi at that measurable rectangle is the following. So you integrate k over, so you just take indicator of dy, indicator of fz, ky dz, and then you need to integrate with respect to nu on the first space. And this simply gives you what? Integral of ky f nu dy, right? Because this is a constant, this is just an indicator, and you integrate it with respect to the measure part of k, so you get k at y and f, and then this is the end result of the inner integral, then you need to integrate it with respect to nu. That was the meaning of this expression. So now we're gonna argue that indeed every probability measure on the product space has this form. Every probability measure on this space can be disintegrated into a measure on the first space, a probability measure on the first space, and the transition probability kernel from the first space into the second. Okay? So first, I'm going to state it as a special case, and then we're going to just write down a corollary for the general case. So let pi be the distribution of the vector yz, namely the joint distribution of y and z. Okay? Assume H is a standard measurable space, And this is not a very bad assumption because this is an image space of a random variable, so it is either some subset of the real line or the Euclidean space in some higher dimension or some function space. And in all those nice cases, it is in most of those cases, it is a standard measurable space. Anyway, so there exists a probability measure nu on E and a transition probability kernel from E to H such that pi is nu cross k. So, moreover, such nu is unique, such k is unique up to nu almost everywhere equality, meaning that if k tilde is another such kernel, then kf and k tilde f as random variables are equal with new probability 1 for every f. For every f. And we should also say, moreover, nu is the distribution of y, and k is the, or let me write it this way, f maps to k, y, f is a regular version of the conditional distribution of y given, of z given y. Z given y. So let's prove it. And then we're going to see why this is a useful theorem. By some examples, we're going to look at that. So the theorem says that we can write the joint distribution of y and z as the product of the distribution of y times the conditional distribution of z given y equals y. This is what this theorem is saying. So we need to find some nu and some k. Nu and k. Okay? I forgot to kernel k, I should say. Right? K. So we need to find the nu and the k. So we need to construct them. But the theorem is already telling us how to construct them. Nu is the distribution of y. Okay? Nu is the distribution of y. So for existence of such a nu, we can simply take nu as the distribution of y, meaning that nu of d is just pi of d cross f for every, d cross h, the full space, right? D in E. Just the marginal distribution of y. Okay? And the theorem also tells us how to construct k. Well, to some extent. It's going to be the conditional distribution of z given y. Of z given y. So since H is a standard measurable space, a regular version L of the conditional distribution of z given y exists. So what does that mean? Well, we pick a set, right? And it's going to give us the conditional. It's going to be a version of the conditional probability that z takes values in f given y. So if we look at it at an omega, because it's a random variable, this is going to be a function of y as we argued before, right? This is going to be a function of y. So let's write it as gf of y of omega. So we have this for each F in H. We have this for some measurable function GF. Now let's try to see it as K of y, sorry, K y of omega and F. So define K y of y and F as GF of y. So we're trying to extract this transition probability kernel, K, but it is almost like L. But we don't see it as a function of omega, but we see it as a function of y. Not y of omega, sorry, we see it as a function of y of omega, or just y. Okay? So we extract, so one needs to check that K is a transition probability kernel from E into H. Right? This is coming from E, and this is coming from H, script H. The important thing to check, so the crucial step is to check, so let's show that pi is nu cross k, where nu and k are defined as above. Let me keep those as a side note. This was from chapter 3. So all we need to do is to check that D cross F at pi has this formula. Because if we can check it for all measurable rectangles, then as they form a pi system, this measure pi is uniquely determined by the values on the pi system. So enough to show that this is the case for all D in E and F in script H. Okay, so let's check it. D cross F. What is D cross F? Well, it is, since pi is the joint distribution of, let me write it this way. Since it is the joint distribution of y and z, we're simply looking at this probability, right? And we can also see it as an expectation of indicator D at y and indicator F at z. What we would like to show is that this can be calculated using the marginal distribution of y and the conditional distribution of z given y. Therefore, we need to condition on y. How can we condition on y? How can we condition on y? So do you remember the tower property of conditional expectation? So you have a lot of conditional expectations nested. So the one that wins is the one which contains less information. So this is an unconditional expectation. It contains no information. Therefore, I can rewrite it as the expectation of the conditional expectation given y. And there is no problem with that, just tower property. Why do I do that? Well, because we want to have the distribution of y and the conditional distribution of z given y. So we need to pass to the conditional distribution somehow, and this is how we're going to do that. Okay, now what should we do? This is measurable with respect to y, so what can I do with that? What can I do with that? Sorry? So how can I integrate this? So what is the relationship between this and the given condition? So this is known with respect to the information given here, right? Therefore, what can I do for that? How can I treat this? As a constant, exactly. So I can take it outside the conditional expectation. So indicator D at y times expectation of indicator F at z and y. Taking out what is known. And this is simply the conditional probability that z is in F given y, right? So how are we going to write it? Well, it's just here. It is ky of F. By construction, right? This is ky of F. So now what is that? Indicator D at y times k of y and f. This is simply a function of y, right? A function of y. So if I need to find the expectation of a function of y, I have a formula, right? So the function at y times the distribution of y over the full space. And since it is an indicator, this is d kyf nu dy, which is what we wanted to show. Right? This is what we wanted to show. So we conclude that pi is really nu cross k. So we showed the main claim of the theorem, disintegration theorem, namely that we can find a measure nu and the transition probability kernel k such that the joint distribution is the product of that marginal distribution and the transition probability kernel. Uniqueness claims I'm going to skip. That was, of course, uniqueness is important in practice, but not extremely interesting. So uniqueness claims are left as an exercise. And then we're done. So there is uniqueness part here. Such nu is unique, such k is unique, blah, blah, blah. So the crucial part is that we can disintegrate the joint distribution into a measure and a kernel. And as a corollary, any probability measure pi on E cross H, script E cross script H, can be disintegrated as pi nu cross k, as in the previous theorem. Of course, assuming that H is standard. Okay. The same assumption must hold, but what I'm trying to say is that this pi doesn't have to be the joint distribution of two random variables, because the reason is that we can always see a probability measure as the joint distribution of a vector. In fact, just take omega as E cross H, F as script E cross script H, pi as P as pi, and Y. So an omega here is what? An omega here is just a pair YZ, right? Therefore, just define Y of omega is Y and Z of omega is Z. So namely that this YZ vector is the identity function, right? Then pi is the distribution of the identity function. So every probability measure can be seen as the distribution of the identity function if you accept to take omega and the image space as the same thing. Okay, so it is from E cross H to E cross H, this vector. I'm taking a special probability measure, not an arbitrary one. And on this space, on this on this choice of omega fp, we can always see this pi as the image of as the distribution of the identity function. So this, in fact, just follows from the disintegration theorem, now that we can see it as a joint distribution. Okay? So you don't have to have pi as a joint distribution because it is always a joint distribution. It can always be seen as a joint distribution. Okay? So at the end of the day, what we have is that every probability measure on the product space can be decomposed or disintegrated into a distribution on the first space and a transition probability kernel from the first space into the second space. And in fact, in the probabilistic setting where we have this pi as a joint distribution, what we have is that the first measure, the measure on the first space, is the distribution of the first random variable, and the transition probability kernel from the first space to the second is the conditional distribution of the second variable given the first one, right? Z given Y, Z given Y. So finally, we should also see how this is useful in computation. So we're going to state a theorem, and then we're going to apply it to some examples, okay? Any questions that you have so far? So the use of those properties are quite important, okay? Tower property, conditional determinism, etc. So these are quite important properties. So let's say we have a joint distribution and we disintegrate it into two parts. So what are we going to do with that? Okay. So let's say we have, let pi be the joint distribution of YZ. Okay. So for every f from the product space that is measurable, we have that the let's say f of yz given y can be calculated as the using the y dz. In other words, if you integrate f with respect to k, this is going to be a function of y. So if you apply y to it, is a version of the conditional expectation of f yz given y. So this integral is simply kf at y, right? So let's check that this is the case. Well, kf of y is a version of this conditional expectation means we need to check two things. So automatically this is kf of y is a function of y. So it is sigma y measurable. So there is nothing to do with that. We need to check the projection property. So we pick a set in the sigma algebra of y. So it is of the form for some d. Just by the definition of the sigma algebra generated by y. So in fact, we have indicator of A is equal to indicator of D at y. Okay. So let's check that projection property is satisfied by this conditional expectation. Okay. Let's check that this satisfies this projection property. So we're going to show that this is equal to kf of y, indicator A. We need to check that these two things are equal. Okay. So let's calculate it. First of all, indicator A is indicator D of y, right? So this is a function of y and z, right? F of yz is a function of yz, and indicator d of y is a function of y. Therefore, the product is a function of y and z together. Therefore, we can calculate the expectation of this using the joint distribution. Yz, indicator d of y, times the joint distribution. Okay, so it's an integral over the product space. But if this is the joint distribution, and we have the disintegration of that, we can use it, right? So if pi has this kind of a disintegration, we can integrate a function with respect to pi by this formula, right? Just nu cross k. So let's use this fact, nu cross k. Let me write here, okay? So this is my function which I'm going to integrate. Now, in the inner integral, this is going to be with respect to the kernel. And in the outer integral, this is going to be with respect to nu. So this function is constant with respect to the inner integral. So it should go out And if we do that, indicator d of y, we're going to get the integral of k, we're going to get the integral of f with respect to k at y, right? F of yz, k y dz is going to give us kf at y. Okay. So now this is a function of y, and this is the distribution of y, function of y, and this is the distribution of capital Y. Therefore, I can see it as the expected value of indicator d at y and kf at y. And this is just indicator of A, so we got what we want. We got what we want because this was the expression, equality, that we would like to prove, right? So something times indicator of A, something times indicator of A. This shows that this is a version of the conditional expectation of this given y. Okay? So we checked that this is a version of the conditional expectation of a joint function of y and z given y. So we can write this formula as fyz given y equals little y is the integral of fyz, conditional distribution of z, given y equals little y. This formula over h. So in other words, conditional expectation can be calculated by integrating the function with respect to the conditional distribution, right? Just like we calculate usual expectations as integrals with respect to distributions, now we do it with conditional distributions. And you can even allow for dependence on y in this function. Oh, okay, we should give a break. 10 minutes.